Most of the matter we see around us is combination of two or more types of atoms. Only noble gases exists as independent atoms in the nature, without combining with any other atoms. In this chapter, we are going to answer the following questions. Why do atoms bond to each other? And why do some type of atoms combine while the atoms of noble gases do not combine with each other? Several theories were put forward to answer these questions. In 1916, a chemist named Lewis postulated that noble gases have exceptionally stable electronic configuration in which they have 8 electrons in the valence shell. 2 electrons in case of helium. This configuration of electrons is called as octet configuration. Because of this exceptional stability, the atoms of noble gases do not bond with other atoms. All the other atoms try to attain the octet electronic configuration either by losing, gaining, or sharing electrons. This is called as octet rule. The losing, gaining, or sharing electrons is nothing but formation of a chemical bond. Chemical bonds are formed to decrease energy and therefore increase the stability. In most cases, atoms only use the electrons in the outermost shell or valence shell in chemical bonding. Lewis also proposed a method to represent various atoms along with their valence electrons that take part in the bond formation. These are called as Lewis symbols. To draw the Lewis symbols for any main group element, we follow these rules. First, note down the A group number for which the element belongs to. This gives us the number of valence electrons in the atom. The A group number is equal to valence electrons. For example, aluminum belongs to group 3A and it has 3 valence electrons. Oxygen belongs to group 6A and it has 6 valence electrons. Nitrogen belongs to group 5A and it has 5 valence electrons. Carbon, 4 valence electrons. The only exception to this is helium. Even though it is placed in group 8A, it has only 2 valence electrons. The second rule is, place one dot at a time on each of the 4 sides of the element's symbol. The dot represents an electron. If there are leftover electrons, keep adding the dots, pairing them until all are used up. Let us do few examples. Aluminum. Aluminum belongs to group 3A, therefore it has 3 valence electrons. So I am going to place one dot at a time on each of the 4 sides of the symbol. So I have 3 separate electrons on aluminum. Next, oxygen. Oxygen belongs to group 6A, so I have 6 valence electrons. First, I place one dot at a time on each of the 4 sides of the element symbol. I have 2 more electrons. I keep adding the dots and pair them. So at the end, I have 2 pairs of electrons and 2 single electrons. Next, we do nitrogen. Nitrogen belongs to group 5A. That means it has 5 valence electrons. You place one dot on each of the 4 sides. I have 1 leftover electron. I pair one of these electrons. So at the end, I have 1 pair of electrons and 3 single electrons. Next, we will do carbon. Carbon belongs to group 4A. That means it has 4 valence electrons. So we place one dot on each of the 4 sides. So at the end, carbon has 4 single electrons. Overall, if we know the group number, we should be able to write the Lewis dot symbol and vice versa. We mentioned earlier that a chemical bond is formed when atoms lose, gain, or share electrons. So the next question is, what type of atoms lose electrons? What type of atoms gain electrons? And what type of atoms share electrons? These questions can be answered based on the periodic trends that we discussed before. Atoms with low ionization energy tend to lose electrons, and we know that the ionization energy increases from left to right and decreases from top to bottom. So, the atoms on the left hand side of the periodic table and bottom part of the periodic table lose electrons. These are classified as metals, as you can see in the periodic table below. Next, what type of atoms gain electrons? Which periodic property do you think can answer this question? Electron affinity. The atoms with more negative electron affinity are more likely to gain an electron. These atoms are on the top right hand side of the periodic table, and we don't consider noble gases. These are classified as nonmetals. The third question, what type of atoms share electrons? For one atom to lose electron, other atom should gain it. For example, if sodium and chlorine were to participate in bonding, sodium is likely to lose electron and chlorine is likely to gain electron, and they are both happy. What if we have a situation where the two atoms participating in the bonding are chlorine atoms, and we know that the chlorine atoms are more likely to gain an electron? Both the atoms cannot gain electrons, so they share electrons. Overall, we can say that when the two atoms participating in the bonding are nonmetals, then the atoms share electrons. Depending on the type of activity that happens during the bond formation, that is, lose, gain, or share electrons, chemical bonds are classified into 3 different categories. First, ionic bond. Ionic bonding involves the transfer of electrons and is usually observed when a metal bonds to a nonmetal. An example could be a sodium bonding to a chlorine atom. Next, covalent bond. Covalent bond involves the sharing of electrons and is usually observed when a nonmetal bonds to a nonmetal. As we discussed earlier, an example could be a chlorine atom binding to another chlorine atom. Metallic bond. Metallic bond involves electron pooling and occurs when a metal bonds to another metal. For example, if you take a block of iron, each of the iron atoms inside the block donates an electron, and all these electrons form a pool of electrons which will be shared by the entire block. Next, we will discuss these bonding types in greater detail. Ionic bond. An ionic bond is formed when electrons are completely transferred from a metal atom to a non-metal atom. The metal, upon losing electrons, forms a cation, that is positively charged ion, and the non-metal, upon gaining electrons, forms an anion, that is negatively charged ion. The electrostatic force of attraction brings the cation and anion together to form a solid compound. One important thing that we need to keep in mind is that the total number of electrons lost by the metal should be equal to the total number of electrons gained by the non-metal. And this is what determines the molecular formula of ionic compounds. That is, in what ratio the metal atoms and non-metal atoms combine. Let us do some examples. An ionic compound formed between sodium and chlorine. Again, remember that the reason the ionic bond is being formed is for participating atoms to get a noble gas electronic configuration. So, let us first write down the electronic configurations of sodium and chlorine. Sodium, atomic number 11. The electronic configuration is 1s2, 2s2, 2p6 and 3s1. The nearest noble gas to sodium in the periodic table is neon, and we know that neon has 10 electrons overall and octet configuration in its valence shell. Sodium has 1 electron more than that of neon. Therefore, sodium loses 1 electron to form a monopositive cation, Na+. For chlorine, the atomic number is 17 and the electronic configuration is 1s2, 2s2, 2p6, 3s2 and 3p5. The nearest noble gas to chlorine in the periodic table is argon, which has 18 electrons and octet configuration in its valence shell. Therefore, chlorine, which has 17 electrons, gains 1 electron to form a mono-negative anion. The total number of electrons lost by sodium is 1 and the total number of electrons gained by chlorine is 1. Therefore, the ratio of sodium to chlorine would be 1 to 1. The Na plus cation and Cl minus anion attract each other to form solid sodium chloride. We can also show this bond formation using Lewis dot symbols. Sodium atom belongs to group 1a, so it has 1 valence electron, so 1 dot around sodium. Chlorine, on the other hand, has 7 valence electrons. First, I place 4 dots on 4 sides of chlorine atoms, and then the remaining 3 dots I will pair them. Overall, it has 3 pairs of electrons and 1 single electron. We can show the electron transfer by an arrow, and it forms Na plus and Cl minus. As we can see now, there are 8 electrons in the valence shell of Cl minus ion, and for Na plus, the valence shell is now second principal quantum number and it also has 8 electrons. One interesting thing about ionic compounds is that even though we write the formula of sodium chloride as NaCl, it doesn't mean that the smallest unit of sodium chloride crystal only has 1 Na plus and 1 Cl minus in it. Ionic compounds usually exist in the form of crystal lattices. Crystal lattices are orderly three-dimensional arrangements of cations and anions held together by electrostatic force of attraction. This is how a lattice of sodium chloride looks like. The green spheres are Na plus ions and the red ones are Cl minus. The image shown here is the smallest repeating unit of a crystal. Imagine this unit repeating itself in all three dimensions to form a single crystal of sodium chloride salt that we use every day. The formula NaCl merely tells that in the lattice, the ratio of Na plus to Cl minus is 1:1. Let us do another example. Formation of the ionic compound between lithium and oxygen. Let us first write down the electronic configurations of lithium and oxygen. Lithium, atomic number 3, and the electronic configuration is 1s2 and 2s1. The nearest noble gas in the periodic table is helium, and lithium has one electron more than that of helium. Helium is the only noble gas that do not have octet configuration. Instead, it has a duplet configuration, which is also exceptionally stable. Therefore, lithium loses one electron and forms monopositive cation. Next, oxygen. Atomic number of oxygen is 8 and the electronic configuration is 1s2, 2s2 and 2p4. The nearest noble gas is neon with 10 electrons. So, oxygen is 2 electrons short of the nearest noble gas. Therefore, it accepts 2 electrons to form O2 minus. Lithium can only lose 1 electron, but oxygen only gains 2 electrons. Therefore, 2 lithium atoms should ionize to satisfy the hunger for electrons of oxygen atom. This is another way of saying that the total number of electrons lost by metal is equal to the total number of electrons gained by non-metal. So, the chemical formula for the compound between lithium and oxygen is Li2O. That is, in the crystal lattice of lithium oxide, we have 2:1 ratio of lithium ions to that of O2 minus ions. The ionic bond formation can be shown by Lewis dot symbols as well. 2 lithium atoms belong to group 1A, so each of them have 1 valence electrons represented by 1 dot. Oxygen belongs to group 6A, therefore it has 6 valence electrons. First, I put 4 electrons on 4 sides, then start pairing them. At the end, I have 2 pairs of electrons and 2 single electrons. I can transfer 1 electron from lithium to oxygen, and the other lithium transfers its electron into oxygen. At the end, I have 2 lithium plus ions with 2 electrons in each, and oxygen 2 minus ion with 8 electrons in them. Both the duplet configuration of lithium and octet configuration of oxygen are exceptionally stable, and these two ions attract electrostatically to form a solid lithium oxide. If we look at the periodic table, overall we can say that each element in group 1A has 1 additional electron than the nearest noble gas. Therefore, they lose it to form monopositive cations. Similarly, group 2A elements have 2 electrons more than the nearest noble gases. These elements lose 2 electrons to form dipositive cations. And group 3A elements form tripositive cations. If we go to the other side, group 5A elements have 3 electrons short of nearest noble gases. So, they usually gain 3 electrons to form a tri-negative anion. Group 6A forms a di-negative anions, and group 7A form mono-negative anions. This information is very useful to determine the chemical formula of various ionic compounds that any combination of a metal and a non-metal can form. For example, let's say you want to determine the chemical formula of the ionic compound formed between magnesium and bromine. We know from the periodic table that magnesium in group 2A loses 2 electrons, and bromine, it is in group 7A, gains 1 electron. So, for each magnesium, we need 2 bromine atoms. Therefore, the chemical formula is MgBr2. A simple way to do this is by using a crisscross method. You write both the atoms, magnesium and bromine, along with their charges, that is 2 plus on magnesium and 1 minus on bromine. And then we crisscross these numbers without using the positive or negative signs. So the overall formula is MgBr2. Let us do another example. What is the chemical formula of the ionic compound formed between aluminum and oxygen? Again, from the periodic table, aluminum belongs to group 3A, so it usually forms a tri-positive cation, that is Al3+. Oxygen belongs to group 6A, and it usually forms a di-negative anion, that is O2-. I am going to crisscross these values without the signs, and the formula for aluminum oxide is Al2O3.